Welcome to my channel. I'm Leo. Today let's do some more LeetCode. So the problem is parallel courses. Forgive me for the background noise because I'm currently sitting in Mountain View Library in California. So there might be some noises in the background, but let's take a look. So you're given an integer n which indicates that there are n courses labeled from 1 to n. Okay, so it starts from 1. You're also given an array relations where relations I equals to previous course and next course. This is a pair. And representing the prerequisite relationship between the course previous course and course next course. Course previous course has to be taken before course next course. Okay. So, in one semester, you can take any number of courses as long as you have taken all prerequisites in the previous semester for the courses you're taking. And return the minimum number of semesters needed to take all courses. If there's no way to take all courses, return -1. Okay, let's look at this. So in this example, the first one, we're going to take 1 and 2. Then we can proceed to finish the course 3. Therefore, we need at least 2 semesters, which means we can take 1 and 2 courses in the first semester. Then we take the third course for the second semester. And let's take a look at the example 2, where 1, 2, 3, we can see there is a cycle in this graph. In this case, we can't finish it because there's a loop, right? We can start from any node, like we can take 2 first, then we can finish 3, and then we finish 1. But then we need to finish 2 in order to finish this loop. But in order to start from 2, we have to take 1. In order to start from 1, we have to take 3, and then in order to take 3, we have to start from 2. So in this case, we can't find a finite number of semesters. So we can't have a loop in our graph. Okay? So how are we going to address this? This looks like something like a minimum height tree or just topological sorting, because it starts from the nodes with no in degree, as we can see. And when we finish this part, we can cut off this pointer. And again, this 3 will have an in degree of 0 at this time, so we can start from the next round. Okay, so it's pretty normal, a topological sorting. So let's start coding. For topological sorting, we have to have the graph. Okay, so now we have the edges here. We can construct the graph, which I will call a adjacency list. Okay, and let's do some looping for if. Let's build a graph. Add a new array list. Okay. Next, we're going to have an array indicating the in degree of each node. So we're going to start calling it in degree and +1 because we start from 1 to n. Okay. So for the relations, our adjacency list will get the prerequisite course and add the edge pointing to the next course. So we have to get the edge 0 and then add edge 1. Okay? And in degree of edge 1 goes up by 1. Okay? So this is constructing the graph. I'm going to comment here, construct the graph, and initialize the in degree array. Okay. Second thing, what are we going to do? We're going to expand everything from it. Okay. Expand the graph. So what do we need? I think first we need to know how many lessons we have learned so far. So if we are unable to finish all the lessons, there will be no result. Okay? And also we are going to record how many semesters are used to fulfill that. Okay, so yeah, that's kind of everything we need. And to do the topological sorting, we still need a queue with integers, so I'm going to call it a queue. And what do we have in the queue? We are going to put all the nodes with no int degree into the queue. So for int I equals to, we're going to start from 1 and to n. If int degree I is equal to 0, we're going to add it to the queue. Then we can do our expansion. While queue isn't empty, first we need to record its size because we don't want to make any confusions with the outer layer and the inner layer. So we're going to record the size equals to queue.size, and so for everything that is in the queue, for every node, if we're going to pop it out, we are going to learn it, right? And we're going to pop it out, pull it out. And what are we going to do next? We're going to cut this pointer off. So for its neighbors, how do we get the neighbors? We have the adjacency list, and we can get all of its neighbors. So how do we cut it? The int degree of each neighbor goes down by 1. And then when this neighbor is, the int degree of this neighbor is cutting down to 0, if int degree neighbor is equal to 0, what do? We can put it into the queue. Okay, so that's good. We pulled this one out, we visited it, and we cut this off, and we can put it into the next queue. We pull this out, we learn it, we detach it from the next course, and now this one can be put into the next queue. Okay, so it's over here. And when this loop is done, we're going to increment the semesters to mark that this layer has been visited. Okay, so now what do we return? We can see if we have learned all the courses. If we learn all the courses, return semesters. If not, -1. Okay, let's try. Okay, I think it passed. So let's do some complexity analysis. So this is like a graph traversal problem. So the only thing we need is the vertices and the edges. So the time complexity is to iterate through all the edges and vertices. As for the space complexity, we used a adjacency list to contain all the edges, and we used a queue structure to contain all the vertices. So it's still V plus E. All right. Yeah, so it passed. Thank you so much for watching. I'll see you in the next video.